Good morning. Welcome to Brandforsk and our result webinar presenting the research project Exposure from Mass Timber Compartment Fires to Facades. My name is Mattias Dahlin and I'm the Research Director of Brandforsk, the Swedish Fire Research Foundation. This project will be presented by Daniel Brandon, Johan Sjöström and Alistair Temple. Would you like to say good morning?
Good morning, everyone. My name is Johan Sjöström. I work at the RISE, Research Institute of Sweden, and together with Alistair, Daniel, and two other guys called Emil and Fredrik, we have been working on this project last fall.
Okay, welcome. Thanks. And Alistair, welcome.
Hi. As Johan alluded to, I'm also a researcher at RISE. I have a background in consultancy and design before joining here, so it's a subtly different background from Johan and Daniel.
Okay, welcome. And Daniel, welcome.
Hi, sorry. Yes, my name is Daniel Brandon. I work also at RISE have been for the last 5 years, and I do mostly research of timber structures in fire.
Okay, very good. So welcome. Now, before we start, I would like to give you a short introduction to Brandforsk in case you don't already know us. We have a vision. We work for a fire-safe society built on knowledge. We develop and communicate knowledge, mostly research, of course, to limit the negative consequences of fire in the society. We started in 1979, and since 2019, we are a foundation. We have supporting organizations that fund everything that we do, and so we are very grateful to them. And since they are a part of different parts of the society, that makes us the collaborations between many parts of the society. The funding so far this year is about 600,000 euro, and we hope to raise some more money before the end of the year. And of course, we use most of the money for research. We do result communication like webinars like this one. We have a research school for practicing fire safety engineers. They do part-time as PhD students for 4 years. And we also have scholarships for students. Now, this is really thanks to all these supporting organizations that we can do this. Thank you very much. And if you are not a supporting organization, please consider to be. That's very valuable and absolutely necessary for us to be keeping on our work. Now the program today looks like this. After this introduction, we will get a presentation of the project, and after that there will be time for questions and discussions. And now we will go to the presentation.
Good morning, everyone. Welcome to the Brandforsk webinar on exposure of modern compartment fires to facades. My name is Daniel Brandon. I work at RISE, and together with Johan Sjöström, I'm going to present the background, the test setup, and the results of this project on behalf of the project team. The Brandforsk project is a supplement to a bigger project that is funded by the United States Forest Service, United States Department of Agriculture. The name of that project is Fire Safe Implementation of Visible Mass Timber in Tall Buildings. Besides the funding of the USDA, there are material sponsors, which are Katara, KLH, Henkel, USG, Knauf, Rotoblas, Boise Cascade, and the Softwood Expert Council. This project has several objectives, but the main objective is the performing 5 real-scale compartment fire tests, which allowed the opportunity to expand the scope and include additional external measurements, which are funded by the Brandforsk project. Today, we will talk about those measurements and also the analysis of those measurements. For some information of the fire scenario, I will also discuss some details of the compartment fire test, but for a very detailed description, you could look on the website shown in this slide. Both tests, the Brandforsk project and the USDA project, have different reference groups. The reference group for the Brandforsk project is organized by Brandforsk and consists mostly of Swedish and American people. A number of compartment fire tests of mass timber structures has been performed before. However, because of recent developments of materials, but also recent new regulations, new tests are needed. And in order to explain what these new developments are, I use an older study as reference, which was led by the NFPA, performed by NRC Canada, NIST, and RISE. This research project had 6 compartment fire tests of 2 configurations shown here. Now I just discussed the ones on the left. You see for this configuration a heat release rate curve of the baseline test, which was a test where all surfaces were protected with gypsum board. I now add the results of the other test where some CLT was exposed, and you see that in contrast with the baseline test where we have a steady decay, there are locations, there are times in which the heat release rate increased, and we know that the movable content of on the floor reduced in combustion rates. That does indicate that the combustion rate of the structure increased at these locations. And it was clear that fire-induced delamination was the cause of this. And during fire-induced delamination, also called glue line integrity failure in Europe, the exposed lamella falls off due to weakening of the bond line, and it exposes a new colder surface to the fire. If the fire temperatures are hot enough, this surface heats up rapidly, chars rapidly, and combusts rapidly. If we manage to avoid this delamination, then we could expect these points to change, and the fire dynamics in the room will change significantly. As a response to this study and also some other studies that showed the same effect, there was a new regulation included in the PRG, a new test included in the PRG 320, which is the product standard for CLT in the US and Canada. In Europe, we expect an annex with a standard test method in the next Eurocode 5. And those both aim to avoid this delamination and subsequently affect the fire performance of CLT in compartment fires in a positive way. So now with the new regulations, we actually need tests that are conducted with materials that comply with these new regulations, and that's why we did these tests. We performed 5 compartment tests, 4 with a relatively small opening and 1 with larger openings. We added a facade extension on all compartment tests to study the exposure of these fires on facades. One of the reasons to perform this research and study the facade fire exposure is that there is an unclear relationship between standard facade fire tests and real fires. Also, the number of compartment fires with essential measurements for comparisons are lacking. We didn't find a compartment fire test with measurements on the facade that correspond to multiple standard facade fire tests. And if we have that data, that would allow us to compare multiple standard facade fire tests, but also to assess whether these tests have a relevant and representative exposure. And then lastly, there have been studies that showed that having exposed wood inside a compartment can have an influence on the external fire plume. However, in those studies, there was no focus on the representativeness of the compartment. We know that, for example, the width of the opening has a significant influence on the fire plume. It is correlated. For slender openings, you can expect higher fire plumes. And therefore, it is essential to test representative compartments in order to have a representative exposure. In response to the gaps that we just showed, we have the following objectives: collect data of the thermal exposure to the external facade in relatively severe fire plume scenarios, compare the exposure to the facade to that of a number of standard test methods for regulatory compliance in North America and Europe, mapping the change of external fire plume as a consequence of exposing larger surfaces of mass timber. In the first objective, I mentioned relatively severe fire plume scenarios, and that needs some explanation. To achieve relatively severe fire plume scenarios, we used statistical data from a recent study in Canada, which are the upper two distribution curves. But we also needed to have information of opening factors, and that we needed to do ourselves. We performed a survey to determine opening factors of about 700 residential and office compartments, and that resulted in this distribution below. With these distributions, we predicted the expected char depth after a fire using a simple parametric fire model. This model is simple enough to perform many times. We performed this calculation 100,000 times, where the computer chose a floor area, fuel load density, and an opening factor randomly, but based on the distributions. So after 100,000 calculations, we got this distribution of the final char depth, and we made sure that our test scenario had a relatively high expected char depth, and we ended up with the 85th percentile value of the expected damage or the expected char depth. The compartment that we chose had the mean value of the floor area according to the Canadian study. We ended up with a 74th percentile value of the fuel load density. And that means if you have a higher fuel load density, we can expect a longer fire. We also had a relatively small opening factor, which corresponded to the 25th percentile value of the whole database and the 7th percentile value of mass timber buildings. And that indicates that in our database, the residential mass timber buildings seem to have higher opening factors. We ended up with a low opening factor because that is the most severe scenario. There we can expect longer fires and higher damage after the fire. So for the small opening factor, we ended up with a small opening factor compartment. We ended up with a small opening factor shown in this distribution. The large opening factor compartment corresponded more with the office compartments that we had in our survey, which are shown in purple here. The test specimen that we have of test 4 corresponds to roughly the center of the distribution of opening factors that we found. For facade fire exposure, we know that the width of openings is important. For slender openings, we will expect a higher fire plume. So it's important to be on the lower side of the distribution of width of openings that we see in real buildings. And according to our survey, we were at the 22nd percentile value of the opening width, which was the 10th percentile value of the opening width for the timber buildings, because they seem to have larger openings in the survey. And this relatively slender opening would result in a relatively high fire plume. Besides having a relatively high fuel load density, a statistically low opening factor, and statistically slender openings, we also had exposed surfaces of mass timber. And that contributes to the fire, which does contribute to a more severe fire scenario. We had tests with surface areas of exposed wood varying from 54 square meters to approximately 100 square meters, which corresponds roughly to 110% to 200% of the floor area. The heat release rate of the fire does correlate a lot with the fire plume height as well. Here we showed the heat release rate per unit area of the different fire tests. And to put that into perspective, we could compare that to some values of the literature. For example, Eurocode recommends a design value of a heat release rate per unit area of 250 kilowatts per square meter, which is quite a bit lower than the values in the table. And that does indicate that we're on the severe side with our fire scenarios. The configurations of the tests were not all known prior to the test series, with the exception of test 1. Every other test had some parameters that were decided in between the tests, and that was the amount of exposed wood and the amount of protection on the protected surfaces. This decision was made between every test based on the performance of the previous test, modeling predictions, and the opinion of the steering group. We started with the ceiling exposed, and then in test 2, we increased that exposed surface areas by exposing the left and the right wall. The rest of the surfaces were protected with 3 layers of gypsum board. In test 3, we only protected the back wall and a portion of the right wall. In test 4, we only protected the back wall, but we only needed 2 gypsum boards in that fire. In test 5, we protected the back wall and 2 strips in the front wall. Here you see some photos during construction. You can see the glued laminated timber beams and the CLT walls. After the walls were assembled, we put on the ceiling. Everything was screwed together. This is a photo from the inside. After the assembly of the main structure, the structure was covered, and we worked mostly on the inside of the compartment. This is a picture of the fuel. What you don't see is that there is quite a relatively big wood crib underneath the table to simulate a heavier table and chairs. We also had wood cribs in the sofa and in all other furniture, such as these cabinets. In total, we had 40% of the fuel consisting of wood cribs, and the rest was residential furniture. Here you can see all tests at the same time, starting from flashover. And you see immediately that after flashover, test 4 starts to cool down. The intensity of the fire reduces, and that would happen slightly later in test 1. In test 1, the fully developed fire was 22 minutes. That was longer in test 2, 3, and 5. And for reference, we added a video made by NIST of a test in the NIST lab of a CLT compartment where that doesn't comply with the current PRG 320/2018 regulations. So here you see the fire of test 1 starting to decay. Test 2, 3, and 5 seem very similar, but they also have relatively similar amounts of exposed wood. And here you can see the difference between the reference test and our tests increasing significantly as this fire doesn't seem to decay. At the end of the tests, the fires decayed mostly. In test 1 and test 4, there was very limited smoldering. In test 2 and 5, there was some smoldering in the walls. And in test 3, we had a reignition of some flaming in the walls. In comparison with our reference test, these results show a much more desirable fire scenario. For the facade fire exposure, it's important to know the heat release rate of the fire, and the heat release rate in these tests were determined from the total mass loss with some corrections of the mass loss of gypsum boards. That is all described in the full report. Here on the left side, you see the mass of the structure during the test, and on the right side, you see the heat release rate of these fires. And you see that the highest heat release rate was seen in the first hour, which is the most important when we look at facade fire exposure. So here you see the same curves with a different time scale. Here are the facades on top of the compartment. You can see from a distance the plate thermometers. We had 4 above every opening, which were installed flush to the surface. Here on the right side, you also see some thermocouples sticking out. These measurements were located in places that match those of standard facade fire tests, which is what Johan will talk about in the next few slides.
Thank you, Daniel, for that. So yes, the positions of the thermocouples and the plate thermometers that we installed were in the exact locations that we could find measurements on from some tests in the literature from other projects. And these tests, in order to have a fair comparison, of course, the facade was not to be included in the fire. So therefore, we needed to find tests that were done on inert or incombustible facades. That was actually quite difficult to find, but we managed to find both from a couple of European tests and from North America. So starting with Sweden, in Sweden we use the SP Fire 105 test, which is a 4 meters wide and a 6 meters tall facade. You can see the size of it here. And these 3 figures in the lower bottom are from this reference here, which is actually one of the 2 references that we use for comparison. So this is actual tests. So behind the flames here, there are plate thermometers that we will compare the results to our test. Here are the flames from 9, 12, and 15 minutes. They seem more or less constant during that period, but shortly after 15 minutes, the test is finished. We move to France, where the Le Pire 2 test is used for compliance to the regulations. And the test setup is a 2-story concrete building where the bottom floor, 2 meters high, has 2 stacks of wood crypts in it and a ventilation opening in the back. We take the data from a publication in 2018 from Effectis. Here is a photo from that actual test. You see a Frenchman overlooking the flames, and here you actually see the plate thermometers installed that we use for our comparison. There's been a drive for decades to come up with a European harmonized method to assess performance of facades in fire, and there is an ongoing project right now to finalizing this method, and it's based on the British method actually. And in this project, there's been some tests on the fire source, the wood crib. So these are some photos from a test series that were conducted within that project. Here is the report. The full facade is not here, but only a few meters above the opening, and behind here there are thermocouples and plates which we will compare to. You see, after 30 minutes there is still big flame from this quite heavy wood crib. And the British method is 6 meters high at least, and it also has a wood crib which is ignited, and after 25 minutes you see a very tall flame from this test. These two photos are from a test on a brick system, and that's the actual data that we use to compare the flame heights between our compartment test and this test method. Moving then to North America, in the United States, the NFPA 285 test is used for compliance testing. And there you have propane gas burners within the burn chamber, and then also a burner at the window. There are two systems being tested, one which passes and one which fails. And when doing these tests prior to installing the facade, you have to run a calibration test, where you have thermocouples on the bare structure here, so the incombustible structure, and those have to follow a certain temperature evolution, and we compare our test to those calibration tests which are defined in the standard. And finally, moving up north in Canada, there's a publication with a test performed on an incombustible facades with thermocouples along the height of this facade, and this is a photo of that particular test after 10 minutes after ignition. Okay, so now it's time to see some results. Here's test 1 and test 2 side by side, just before flashover. So test 1 has about 54 square meters of exposed mass timber. That's the whole ceiling and the beam. Whereas in test 2, you have the ceiling, the beam, and 2 walls. But just at flashover and shortly beyond it, the two tests seems to be very, very similar to each other. You see a very heavy flame ejected through the opening. You see our plate thermometers here, sometimes visible behind the flame. You also see that there was virtually no wind during the test. Here's a photo just after flashover for all the 4 tests for residential buildings. So test 1, 2, 3, and 5. They all seem to have a very similar fire plume ejected from the openings. In test 5, you see we had an accident with our mock-up facade just the weekend before the test. There was no time to repair it, so we have only measurements on one side and only to a certain height. But this test is very similar to both test 2 and 3. Looking at the test, which resembled an open plan office space, we see that directly after flashover there was a very vivid combustion, and we had openings on all these 3 sides with massive flames coming out. But actually only, as you also saw from the heat release rates that Daniel showed before, only 4 minutes after flashover, the flames are significantly reduced, only stretching, in this case, between 0.5 and 1 meter above the opening of the compartment. So on to the actual exposure to the facades. We look now at these 4 plate thermometers that were installed above each opening. Here's graphs on the fully developed phase for the tests. This is average of both sides. We see test 1 reaches maximum quite high, quite rapidly, and then there's a continuous decay, whereas test 2, 3, and 5, where we have much more mass timber exposed, there's a longer period of constant exposure to the facade. And again, test 4, the office space does not reach the same temperature in the beginning, and then clearly decreases rapidly after a flashover. There are different ways of expressing thermal exposure. Actually, the term isn't really defined. One way to do it is to use the adiabatic surface temperature, and from these tests, we can see in this graph here, the red curve is the plate thermometer, one of the plate thermometers in test 2. The dotted blue line is the small thermocouple next to the plate. The dashed line is the temperature behind the plate, and from these we calculate the adiabatic surface temperature of the surface, and that's the black line, which we see more or less is overlaid on the plate. So in the future, we only look at plate thermometer temperatures and say that they are basically identical to the adiabatic surface temperature. In addition to plates, which is a good indicator of thermal exposure, we also had small thermocouples, and the reason was because the test data that we compare with, most of them only use small thermocouples. So in this slide, this is the maximum 5-minute average of all the thermocouples at a specific height. So at 2 meters height in test 4, the maximum 5-minute average of the test is 430 degrees. So 5 minutes we used for the residential buildings, and actually only 3 minutes for the short office space. So what you see is that the temperature decreases with height, more for the office space than for the residential buildings, and that could be fairly described by something which looks linear. And also we can look at the effect of increasing the areas of exposed mass timber. So in test 1 here, with the ceiling exposed, we have about 53 square meters of exposed timber. In test 2 and 3, this is increased to about 91 and 97 square meters, which is an increase by roughly 20 to 80%. And what happens then is that we see an increase in temperature on the facade between 100 and 130 degrees. Alternatively, you could say that in order to reach the same temperatures in test 1 that you have in test 2 and 3, you have to climb between 0.65 and 0.85 meters up along the facade in order to reach the same temperatures. And this height difference is something that you might be able to see in the flame height of the recording. So we had an automatic image analysis routine where we evaluate the flame heights of the test, and we see that in our test they vary between 3 and just over 4 meters. Test 2 had the highest flame height, and test 3 had the lowest, and test 3 was the only test where we actually had a slight influence of wind, which you actually could see reduced the height of the flame. But the most significant effect of exposing more mass timber surfaces was the increase. So in test 1, with the ceiling exposed, we had a 22-minute of the fully developed phase, whereas in test 2, 3, and 5, there are about 30 minutes. So that's an increase of about 30 to 40%. And the office building, of course, is very, very short still. Okay, on to the actual comparison between our compartment tests which are severe and representative of mass timber buildings, and the compliance test used around the world. So we start with NFPA test in the United States. We see that the calibration curve there is actually meant to simulate somewhat of a time temperature curve from a fire resistance test, so it increases throughout the test. It has a similar length of fully developed fire as our test, and the average temperature during the test compares pretty well to our test one, the one with only the ceiling exposed. We also see that the variation of temperature with height corresponds well to our compartment tests. Moving to Canada, we notice that the growth in the Canadian test is faster than the NFPA test. So it reaches high temperatures more rapidly. However, it reaches its maximum after only 20 minutes, followed by a decay. And generally, at least further up on the facade, so this is 1.5 meters, 2.5 meters, and 3.5 meters above the opening. And the further you go, the colder the temperature of the Canadian test is compared to our compartment test. And generally, we see that it agrees with our test one after about 15 minutes after ignition. In Europe, the BS 8414 test used in UK showed a close resemblance of the PT temperatures, the plate temperatures of the test and the compartments. So we see that it has more or less the same duration and more or less the same exposure. On the other hand, we see that the thermocouple temperatures, so the small thermocouples that also are installed on the facade, they show high temperatures in the test compared to the compartment test. And the reason for that is that in the compartment test, we have a very big flame, which is ejected maybe a little further from the facade. So not the thermocouple maybe not at every instant picks up the warmest gases. However, we have a lot higher radiation from the compartment test. So in the end, the plates, which is a good representative of exposure, are very similar, even though you see a difference in the thermocouple temperatures, the small ones. The flame height is for the British test alongside the highest of our compartment tests. And the proposed European method is very, very similar to the BS 8414 test, and therefore we see that if we take the average of the gray ones here, which are the test method, and our compartment test, they actually fall within plus minus 100 degrees of each other. If we look at the Le Pire test in France, we notice that the high intensity phase of the test is about 17 minutes. And that's actually not far from what we expect from our compartment test if we would have no visible surfaces of mass timber. We also see that the shape of the temperature evolution is quite similar to our compartment test. However, the temperatures here at 1.3 meters and here at just over 2 meters are significantly lower than what we found from our compartment tests. Several hundred degrees lower, actually. The Swedish SP Fire 105 test has also much lower temperatures, maybe a bit higher than the French one. However, we notice that the duration of the fully developed phase is only 10 minutes, so very far from what we see from our tests. The flame height, however, is around 3 meters, which is in the lower part of ours, so that's not the difference there is not so striking. And finally, our last results is looking at the incident radiating heat flux away from the openings. So most countries have regulations concerning what you can expect in terms of radiation to the next building. We assess that at 4.8 meters and at 8 meters from our openings. And we do that, and then we have juxtaposed some of the limits defined in Sweden, 15 kilowatts per square meter, and also 12.5, which is the limit in UK and also the NFPA code. We notice that at 4.8 meters, we exceed these limits in most of our tests, whereas at 8 meters, there is a good margin towards these limits. So trying to conclude this, we have now data on the thermal exposures to facade from representative and severe mass timber compartment fires, and this can be downloaded from our project website. We notice that the standard test methods that are used for regulatory compliance, they differ significantly in thermal exposure to the facade between them, both within Europe and between North America and Europe. However, so does the assessment criteria that are associated to each method. So this is no evidence that any method will pass safer solutions to the market than any other. We can conclude that the BS 8414 method and the proposed European method, they are at the evaluated heights from this study, very similar in thermal exposure as the most severe mass timber compartment test that we performed. The NFPA and the Canadian test, they are similar to the test that we performed with a full ceiling exposed, so test 1. The Lepier 2 test and the SP Fire 105, they show clearly lower temperatures on the facade than our compartment test. And SP 105 also has a very short duration in comparison to the compartment tests. And finally, for these tests, if we increase the area of exposed timber by about 70 to 80%, which is just over the floor area of the compartment to roughly twice the floor area of the compartment, we increase the duration of the fully developed phase by 30 to 40% roughly, and the temperatures on the facade by 100 to 130 degrees, as defined by thermocouple, small thermocouple measurements. So the report and the data are available at our project website, and also at the Brandforsk website, you will be able to download the report. I included a figure here of pre-flashover in test 1, where you actually see flames going out even before you have a fully developed fire. And we'd like to say thank you to our funding sources. So Brandforsk sponsored all this analysis of the facade and the building of these mock-ups, and of course to our international funders for performing the whole test program. So if you have any questions, we'll be happy to answer them. And if you think of something later, you can contact us via email. Thank you very much.
So, thank you. We already have a lot of questions, and I think that we will soon have even more. And I think that maybe we should start with the delamination. It was mentioned quite early in the presentation, and we have a couple of questions about that. And when I was in carpenter school in the 1980s, we were taught not to glue wood like this, crosswise, because it moves like this and it will fail. And I guess wood is the same as in the 1980s, but maybe glue has changed, or how come one think that this is possible now?
I think I can answer this. So it's important to realize that CLT, before it's actually put on the market, it needs to go through a big number of tests, which includes a test exposed where the element is exposed to different environments, dry and wet, and it shouldn't delaminate during those tests. But it is what I think the reason for an increased challenge in fire. And if you glue lamellas parallel to the grain, so we know that the biggest shrinkage is perpendicular to the grain. If my fingers would be the grain, and you glue something with the same direction and you shrink it, there is no sliding between my fingers. There's no additional shear stress. If you do that perpendicular, there will be an additional shear stress. So these adhesives, they do seem to prevent it in situations without fire, and with fire you need basically to look at better performing adhesives to avoid this issue. So that was the step progress in the last few years. These adhesives do exist. It's not just a matter of adhesive, it's also a matter of the thickness of the lamella we found. But it is, yeah, I guess it is the difference between CLT and glue lam in fire.
Okay, so how, I think you mentioned is that you have different adhesives. Is there different glue used in North America and in Europe, for example, and how come?
Well, yes, usually, well, the market is different, but there are adhesives that are being sold in the US and Europe, but they have different, well, different test standards and different certification criteria. And I know the adhesive that we used, I guess it's not yet on the market in Europe, but it might be in the future.
Yeah, very interesting topic. I think we can have a single webinar about just delamination. But moving on, you also mentioned the fire load and the heat release rate and the heat release rate per unit area, and I would like to discuss that a bit. And starting with the fire load, what difference does it make? What fire load you have in an experiment like this?
Well, the fire load has, I think, there are two important aspects. How long does a fire last, and also how intense is the fire? And I guess the more intense your furniture, etc., the more intense it burns, the shorter your fire will become, because you release more of the heat in a shorter period. So the fire load will, if you have a higher fire load, you would naturally prolong the fire, but it's not the only aspect. It's also how fast is your fire load burn, which is important.
Yes.
And
did you include the CLT and the glue lam in the fire load here?
It depends on which slide you were talking. Is it the heat release rate per unit area you talked about?
No, but a fire load.
The fire load, no. It's so the fire load in the statistical analysis is just the movable fire load, which is the furniture, etc. So we determined that, and then we added in the test the CLT.
Right.
Yes.
Okay, thank you. And we also have a question about the heat release rate. How did you measure that?
Yeah, so we calculated it from the mass loss rate. So we had the mass of the floor measured, the mass of the structure. We had to perform corrections for the mass loss of gypsum boards, and also a correction of the mass loss of the facade itself, because that is non-combustible. It just dries out. I think it's quite difficult to go into full detail, but the project report of the compartment tests actually goes into this in detail.
Yes.
But we could also mention that it's not we don't measure a heat release rate per se. It's a mass loss rate,
Right.
and we don't know, of course, how much is combusted within the compartment and how much is combusted on the outside. But of course, we see from the videos and from the results that if you have a higher mass loss rate, you will also have a higher plume, because we cannot have more oxygen into the compartment than our limits from the openings.
Yeah, yes, it's quite difficult to know. I don't think it's possible to actually measure how much of the heat is released inside and outside, but you do have these relationships, empirical relationships from the past, and they would indicate that roughly 15 megawatts in the small opening compartments, 15 megawatts would combust inside. That would mean that the rest combust outside.
Yes. Right. Thank you. And yes, we should go to the facade, but let's stay in the room just for one more question, and that's the heat release rate per unit area. You mentioned that in the Eurocode it's about 250 megajoule per square meter, but you had more than twice that. And how, for a designer, for example, what does this mean when you get a more intense heat release rate per unit area like this?
Yes, first of all, it's good to mention that the heat release rate per unit area varies quite a bit. If you look at literature, there has been a paper by Danny Hopkins about it recently. So it is a variable. It's good to actually get the right number for your design. However, I should also say that the Eurocode 5 value is, I think, used to calculate the fire curve, the temperature curve, and that would mean the duration, and in case of a fuel-controlled fire, also the temperature. And in that case, it's actually conservative to choose a low number, because a low number, a conservative number, would mean you have a longer fire exposure in your design. So for that purpose, you would need to choose a conservatively low value. For the facade design, you want a high value. So if you would use this Eurocode value for facade fire exposure, I think that's more difficult to defend it. I think you should choose a higher number. But that said, I do think it's still relatively high in comparison to that of the literature, and that would indicate. So it's just used to indicate that we have a relatively severe fire plume scenario in front of the facade.
For facade exposure, it's very difficult to balance the duration of the high intensity and the actual intensity that you have. It's a little easier for a timber compartment than duration is a problem. But for a facade, you don't really know. It depends a lot on the actual facade system itself, how it responds, not only what temperature it does, but what happens to the facade.
Yes, right. Let's leave the room and go out to that facade. And when you compare this, and how did you define flame height, for example, when you try to measure the exposure?
If we can share my screen, I've got a little image which shows some shots. That's sort of a brief overview of how we did it. So one of the other guys involved in the project actually did this work for us. So we should probably credit Emma with the hard work that went into it. But in essence, we took the frames from the videos and converted them into a grayscale image, and then from there into black and white. And that allows us to define the sort of the flaming regions. And then at each step, we took whatever the highest, the tallest consistent flame was that was emanating. So for the example that we've got here, you can see there's two small bits which are broken off at the top. So we ignored them, and you can, with the red box, we have the area that would be chosen for this particular frame. And then there is we know the height related to each pixel, or close enough. It'll be slightly distorted from the angle, but it's reasonably good. And then so that gives us the height of the flame up to a limit, so that there are a small number of flames on a couple of tests where it just exceeds the limit, I think, but it's not very often that it hits the top.
And it's 120 frames per second, so it's a lot of frames.
Okay, thank you. And this was you compare this to test, for example, and it was many of the tests you ran here had quite a strong exposure to the facades. Do you think you need to how to deal with that? Do you think that buildings like this needs another design, or that the test methods needs to be changed, or?
I mean, that's it's difficult because if you have different assessment criteria, then of course you can have different exposures. So if you say that you're not allowed to have flames further than this much, then you can have a quite small exposure. And if you allow a lot more, then you would need a more realistic exposure, of course. But setting these criteria, that's very difficult. I mean, we're trying to do that currently with the new proposed European method, and it is very demanding to say what is acceptable and what is not. Normally, we have already something in the society, and we say, is the society happy with this? And then we don't want to change it to something worse. And if the society becomes unhappy, as usually after some sort of event, then we try to increase these assessment criteria. So for these, it's very difficult. I've seen many SB Fire 105 tests, and the systems that passes usually they perform well, basically, they do. But in terms of harmonization, this could be a big problem, of course, because for different countries, it could be very difficult. And then the compartment test that we did here, that's mass timber compartments, which means that we have a lot more fuel exposed, which means that there will be a bigger flame on the outside. And the question is, for what system, for what types of buildings do we want compliance to facade tests? If you have a really, really tall building, you need an incombustible facade anyhow. So it's actually very hard to say, and it's mostly up to the authorities and regulators in each country to say what feels good. Are we happy with this level of safety? Because it's virtually impossible to quantify it. This is, however, one step forward to quantifying at least the exposure.
I think the other thing is, as well as Johan touched on there, is that these are fires for mass timber exposed mass timber buildings. So designers and approving authorities and wherever it is need to think about the building that they are doing, and therefore, does this fit within the framework of our regulations as they've been designed and built up? And you might look at them and go, actually, for where I am in the world, and where this building is, this building is actually totally unlike what the regulations assume the building that you're building are, and therefore maybe we using just standardized tests, be it for facades or be it for any other aspect of the building, isn't necessarily appropriate. And so that's something that should be happening on every building everywhere, and most buildings are pretty normal. And so most buildings, you probably don't need to worry about tests like this because you don't have vast quantities of mass timber. But when you do have something a little bit unusual, you need to think about how is that going to change how the fire is going to behave, and therefore how do we need to change our design to take into account and what bits of evidence are there around how this change might impact. And that's sort of where this experiments like these help out, because they give that data point for designers when they come across something a little bit unusual, and therefore have something that they can look back and use as a basis for whatever it is that they decide that is appropriate for their building.
Yeah, right. So the design goal may differ, but and
yeah,
that's not your research. Your research is more the exposure. So.
Yeah.
Okay. Talking about measurement and exposure, we have a question here about if you calculated the radiation. You mentioned in the presentation that the different kind of measurements gave you different results, and whether the flame was close to the facade or a little bit out from the facade, and also that the plate thermometer was probably the best way of measuring this. And I know that you can probably calculate the radiation. Did you do that, and is it available in the data set?
The radiation per se to a plate which is engulfed in flames is not a very relevant entity. I mean, first, it's very, very difficult to calculate what of the heating of this surface is due to convection and what is radiation, because you don't know the velocity and you don't know the temperature of the gases and everything. So that is trying to separate those two is not really helpful. But what I can say is it gives you an exposure, and that could be represented by the adiabatic surface temperature, which is the highest temperature that you can reach given that exposure that you have at that moment, for something which has the same emissivity as this plate. And the thing is that it's a surface will behave a lot differently compared to a small little thing which sticks up, because this small thing is highly sensitive to gas temperatures and gas velocities, whereas the surface, a plate will represent basically what the surface will experience. Then of course, not foolproof, not 100%, but it's the best robust assessment that we have, I would say.
All right, thank you. And the computer sets, will they be available if someone would like to study them more?
The data, yes, yeah. I don't know if we've already finished. At least, is it on the web page?
No, it's not. It will be on the web page today. So I
Yes.
just need to upload it. Yes. So after this presentation, I will do it.
Yes. So there's a spreadsheet with 4-second, basically 4-second
intervals
for all the channels which worked. Anyone who's done fire testing knows that some of them fail.
Unfortunately, not always the same ones for all tests. So sometimes you have ones working 3, and then in the 4th one it's just not there. But such as fire testing.
Okay, thank you. Now, if you would like to give some advice to different attendees listening today, let's say for fire safety consultants and designers, and what would you? How can they use the results from this work?
I think the main impact this project could have is actually being a guidance towards standard facade fire tests. But if you want direct to use this data directly, it's more a reference point for performance-based design. So if you have performance-based method, you could test your method against these results as some points of validation.
Okay.
Yeah. Knowing the exposure makes it easier. If you have a test where you have an exposure which is representative of a real case, then it's easier to set your assessment criteria. If you want to downscale it, it's much more difficult. So that is something, and we've seen now that the North American test, the British test, and the proposed European test, they all fall within what could be considered severe and representative, at least.
But not the Swedish test?
No, not in terms of exposure. But then, of course, you have to balance against what the assessment criteria are.
Yeah. Okay, so if I would ask you the same question, but for let's say someone listening now developing constructions like this, CLT buildings or glulam, do you have any advices to them how to use this?
Make sure you fill all the gaps.
Yeah.
Yes.
Yes, I think it's good to. So there are also countries where it's not required to actually avoid delamination, but you can just choose to do it by choosing a product with a better performance. That would be my advice in those countries. And in some countries it is regulated already. In other countries you need to take this initiative yourself.
Okay, right. And any advice to yourself? Further research on this, or maybe further development of testing methods, or I mean, like, what should researchers do next on this topic, do you think?
Well, there could be much more parametric studies on facade exposure, and also I think what we did with the survey of these 700 something apartments, that was very interesting to see what's actually is out there for buildings no more than 10 years old, because that kind of, and then adjusting what we do as researchers to what's actually the statistics, which is actually in our reality. That's that was a good thing, and I think we need more studies basically on just assembling data. That is very valuable when you want to know that what you're doing is reasonable.
Yes. I just have a question about that, about those 700 something compartments. And when you did that analysis, was it for floor area for the total residential unit, or room added, or was it for individual rooms within the residential unit?
It was total residential unit. So it was based on publicly available floor plans, primarily via planning portals in the UK. So in the UK, they have to publish the plans for any new building publicly, and so a lot of these are relatively easily large searchable databases to find residential buildings of the scale that you want. So it's mainly UK buildings, some from the US, and maybe a small number from Sweden as well. I can't quite remember if we managed to find many.
Norway and Austria.
Yeah. So and then the mass timber buildings were a bit more spread out because there's less of them, particularly large ones. So they were easier to pre-identify rather than scrolling through lots of planning submissions on portals. But yeah, we didn't have any, as a result, we didn't really have any sort of fire compartment plans or anything. So we had to make assumptions about the internal walls and stuff. And generally, fire compartments in residential buildings are put around the residential flat, and the internal walls are relatively lightweight and without much in the way of fire resistance. So the safe assumption was to assume that they didn't provide anything, and that gave us an easier standard working point. And then we took the whole floor area of the flat and then any windows opening into them.
Right, thank you. We get a number of questions about if you have a combustible facade, a wooden facade, for example, I mean, what would happen in tests like this if you had a wooden facade and if you had some kind of treatment to that facade? And I know you didn't do those tests, but
well,
what do you think would happen?
Yes, well, I can comment on it because it's not my own work. It's from my colleagues. Yes, so if you treat a wooden facade, it can be quite sensitive to weathering, and actually it's quite difficult to get treatment that doesn't decay fast through weathering. So it is important to look at both aspects. What is the performance? Not only what is the performance before weathering, it just needs to be shown somehow that it can withstand weathering and then still perform well, improve the performance of the wooden facade. And there is a standard test method for it at the moment, but it's not required to use to perform weathering on a facade test before you test it. So I think it's two separate standards. One is a test standard, and I'm now talking about Europe, and I'm sorry, I don't know the number of the test standard by from the top of my head, but there is one where you have to apply weathering and then perform a small scale fire test to show that your treatment can be used on exterior wooden surfaces.
Yes, right.
Yeah. I suspect that most anything that was combustible, though, if it had been exposed to some of the exposures in some of our large tests, they probably wouldn't necessarily stand up very well. So I guess it's a case of think about what system you're using and where you're using it and what scenario you're using it, and is it appropriate? And if you've got a 2-story building, it's probably okay if you're, in terms of life safety, if your facade, if you have a fire like this and then it lights your facade, if you got a fire like this, your building might well be gone anyway, in terms of if it's a small 2-story one, so your facade damage probably doesn't matter. But don't then go and use the same facade on a 25-story tower, because then it's suddenly less appropriate and you have significantly more life safety impact if your facade burns. So it's as with lots of things in fire, I think in design, it's make sure that you're using the appropriate test results for the appropriate times, appropriate systems, and think about how it all works together rather than necessarily does one individual thing tick the right box in one point and in isolation.
Yeah, that's true. Very wise. And I mean, you had flames about 3 meters high, and usually you have a window within that.
Yeah, so that's
there's a risk, of course, of spreading fire through the window to the next floor, and then that catches fire and spreading it further on. Again. So, as you say, we have to see the whole picture.
And the details around the window, because even if your window glass maybe survives, you need to make sure your detailing around the window is going to resist, and you don't get fire entering cavities through that point and all sorts of things like this. Or if you've got and now the words are gone from my head because it's been a few years since I've done any design, but where if you've got an air gap in your facade, and you often need points to let moisture out and things like that, so you need to think about where they are and how they're designed and whether they might be an entry point for fire. And lots of detailing in a facade that needs to be thought about.
Yes. And we have a question about how to prevent those flames to occur in the first place. And one suggestion is using a sprinkler system within the compartment, of course. Have you an experience I do know you have a lot of experience. Do you have an experience about the effect of sprinkler in a compartment like this?
Well, yes. Well, the purpose of sprinklers would be to limit the development of the fire. So I guess if a sprinkler functions properly, it should never become such a large fire. That's the purpose of having sprinklers. The reason why we look at it, we do recommend sprinklers in well, most tall buildings anyway, but we also need to take into account the scenario, and it's quite an unlikely scenario, but you still need to take into account that sprinklers do not work. And statistics about sprinklers seem to be different in different countries, but it seems to be up to 10% of the situations where sprinklers do not work in some statistics. So it needs to be taken into account.
Yeah. So yeah, and I guess all systems need thoughts about redundancy, for example.
Yeah, and active systems like sprinklers and things, and passive systems as well to an extent. They're very reliant on proper maintenance and things like that, which is why, yeah, I can't remember exactly what the source of it was, but when I was working in consultancy in the UK for residential sprinkler systems, we generally assumed a reliability of around 90 to 92%, because they tend to have a lot less maintenance and care and things looked after them, and whereas commercial systems for office buildings and things tended to be closer to 98, 99%. But yeah, like it is heavy reliant on the system being maintained and you having appropriate linkages to your water mains and all these sorts of things. And so what happens, for example, in a situation where they're doing work on the street outside and they've disrupted the water's off for an hour and a half. It's very unlikely when you start accumulating these sorts of coincident events, but these scenarios do need to be thought about to an extent.
Yes, thank you. And I guess I mean the main project that you did here was about having exposed timber in compartments, and I think that's a trend that we can see in most countries that use mass timber buildings. So I guess this is a scenario and something to think about in countries using this technology. Well, thank you very much. I think we have covered the questions, and I think it was really interesting to hear the presentation and to have this discussion with you. And I believe that this is not the end of this topic. I think it will have a lot of work in the years to come as well. And of course, the larger project that this was attached to, I guess, can also be read and discussed further on. So thank you very much. I would just like to wrap things up before we end. So thank you, Daniel and Johan and Alistair.
You're welcome. Thank you for hosting us.
Thanks.
Thank you to the audience for all your good questions. And if you want to attend more Brandforsk webinars, you can find them at our website. You can also learn about them by following us on LinkedIn or register to our newsletter. And you can register to that at the bottom of our website. The webinars to come in May are in Swedish, but there are plenty of time for you to learn, about a week at least. We also have a YouTube channel, and you can find earlier webinars and also recorded seminars that we've had. And of course, before we close, I would like to to acknowledge and thank my colleagues, Francis Renius and Mattias Hamrin, that have been producing this webinar. Thank you very much. And thank you again to all our supporting organizations. So, and please answer our questionnaire after the webinar. That's very valuable for us. And I hope to see you soon again on our webinars. And also, please feel free to get in touch with us. You can find our contacts on our website. Thank you. Bye-bye.